Vincent Boucher, founding chairman of Montreal.AI. Our participants tonight are Professor Gary Marcus and Professor Yoshua Bengio. Professor Gary Marcus is a scientist, best-selling author, and entrepreneur. Professor Marcus has published extensively in neuroscience, genetics, linguistics, evolutionary psychology, and artificial intelligence, and is perhaps the youngest professor emeritus at NYU. He is the founder and CEO of Robust.AI and the author of 5 books, including The Algebraic Mind. His newest book, Rebooting AI, Building Machines We Can Trust, aims to shake up the field of artificial intelligence and has been praised by Noam Chomsky, Steven Pinker, and Garry Kasparov. Professor Yoshua Bengio is a deep learning pioneer. In 2018, Professor Bengio was a computer scientist who collected the largest number of new citations worldwide. In 2019, he received, jointly with Geoffrey Hinton and Yann LeCun, the ACM Turing Award, the Nobel Prize for Computing. He is the founder and scientific director of MILA, the largest university-based research group in deep learning in the world. His ultimate goal is to understand the principles that lead to intelligence through learning. This diagram shows the architecture of a 2-layer neural network. According to Geoffrey Hinton, you have relatively simple processing elements that are very loosely models of neurons. They have connections coming in, and each connection has a weight on it. And that weight can be changed through learning. Deep learning uses multiple layers of processing units to learn higher representations. Professor Marcus thinks that expecting a monolithic architecture to handle abstraction and reasoning is unrealistic. Professor Bengio believes that sequential reasoning can be performed while staying in a deep learning framework. Our plan for the evening. An opening statement by Gary Marcus and by Yoshua Bengio, followed by a response. An interview with Yoshua Bengio and Gary Marcus. Then our guests will take questions from the audience here at MILA, followed by a question from the international audience. This AI debate is a Christmas gift from Montreal.AI to the international AI community. The hashtag for tonight's event is AI debate. Montreal.AI is grateful to MILA and to the collaborative Montreal.AI ecosystem. That being said, we will start with the first segment. Professor Marcus, you have 20 minutes for your opening statement.
Thank you very much. And of course, the AV doesn't work. Hang on.
So it's.
You need an update on.
No, don't worry about that.
Do we have another device here?
Yes, we'll do it from this one, and that will be fine. No, that's fine, that's fine.
Before we started, Yoshua and I were chatting about how AI was probably going to come before AV, and he made some excellent points about his work on climate change and how if we could solve the AV problem, it would actually be a good thing for the world. We skipped the first slide. Skipped the first 2. Are we good on sound? So this was Yoshua and I last week at NeurIPS at a party, having a good time. I hope we will have a good time tonight. I don't think either of us is out for blood, but rather for truth. An overview of what I'm going to talk about today. I'm going to start with a bit of history and a sense of where I'm coming from. I'm going to give my take on Yoshua's view, which I think is actually more agreements than disagreements, but I think the disagreements are important, and we're here to talk about them. And then my prescription for going forward. The first part is about how I see AI, deep learning, and current machine learning, and how I got here. It's a bit of a personal history of cognitive science and how it feeds into AI. And you might think of it as, what's a nice cognitive scientist like me doing in a place like Mila? So here's an overview. I won't go into all of it, but of some of the things that I've done that I think are relevant to AI. An important point is I'm not a machine learning person by training. I'm actually a cognitive scientist by training. My real work has been in understanding humans and how they generalize and learn. And I'll tell you a little bit about that work going back to 1992 and a little bit all the way up to the present. But first, I will go back even a little bit before to a pair of famous books that people have called the PDP Bibles. Not everybody will even know what PDP is, but it's a kind of ancestor to modern neural networks. Vince showed one, and Yoshua will be talking about many. And the one I have on the right is a simplification of a neural network model that tried to learn the English past tense. And this was part of a huge debate in these two books. I think the most provocative paper, certainly the one that has stuck with me for 30 years, which is pretty impressive to have a paper stick with you for that long, was a paper about children's over-regularization errors. So kids say things like braked and goed some of the time. I have two kids. I can testify that this is true. And it was long thought to be an iconic example of symbolic rules. So that you'd read any textbook up to 1985 and it would say, children learn rules. For example, they make these over-regularization errors. And what Rumelhart and McClellan showed brilliantly was that you could get a neural network to produce this output without having any rules in it at all. So this created a whole field that I would call eliminative connectionism, which was using neural networks to model cognitive science without having any rules in it. And a so-called great past tense debate was born from this. And it was a huge war across the cognitive sciences. By the time I got to graduate school, it was all that a lot of people wanted to talk about. On the one hand, up until that point, until that paper, most of linguistics and cognitive science was couched in terms of rules. So the idea was you learned rules like a sentence is made of a noun phrase and a verb phrase. So if you've ever read any of Chomsky, a lot of Chomsky's early work looked like that. And most AI was also all about rules. So expert systems were mostly made up of rules. And here Rumelhart and McClellan argued we don't need rules at all. Forget about it. Even an error like braked might in principle, they didn't prove it, but they showed in principle, might be product of a neural network where you have the input on the bottom, the output on the top, and you tune some connections over time, might in principle give you generalizations that look like kids were doing. On the other hand, they hadn't actually looked at the actual empirical data. So I trundled myself off to graduate school to work with Steve Pinker at MIT, and what I looked at was these errors. I did, I think, the first big data analysis of language acquisition, or one of the first ones writing shell scripts on Unix Spark stations, and I looked at 11,500 child utterances. And the argument that Pinker and I made was that neural nets weren't making the right predictions about generalization over time and particular verbs and so forth. If you care, there's a whole book that we wrote about it. And what we argued for was a compromise. We said it's not all rules, like Morris Halley, who was on my thesis committee, liked to argue. And we said it wasn't all neural networks like Rumelhart and McClellan did. Instead, it was a hybrid model. We said best captured the data. A rule for regulars, so walk gets inflected as walked. If you add this ed to the past tense. Neural networks for the irregulars, so this is why you say sing, sang, but might generalize it to spling, splang, that sounds similar. And then the reason children made over-regularization errors, we said, is the neural network didn't always produce a strong response. If you had a verb that didn't sound like anything you'd heard before, you'd fall back on the rule. So that was the first time that I argued for hybrid models back in the early 1990s. In 1998, or even a little bit before, I started playing a lot with the network models. There had been a lot written about them, but I wanted to understand how they work. And so I started implementing them, trying them out, and I discovered something about them that I thought was really interesting, which is people talked about them as if they learned the rule in the environment, but they didn't really always learn the rule, at least not in the sense that a human being might. So here's an example. If I taught you the function f of x equals x, or you can think of x equals y plus 0, or different ways to think about it. So you have input like 0, 1, 1, 0, a binary number, and your output is the same thing. And you do this on a bunch of cases. The neural network learns something, but it also makes some mistakes. So if you give it an odd number, which is what I have there at the bottom, after giving it only even numbers, it doesn't come up with the answer that a human being would. And so I describe this in terms of something called a training space. So let's say the yellow examples are the things that you've been trained on, and the green ones are things that are nearby in space to the ones you've been trained on. The neural networks generally did really well on the yellow ones, and not so well on the ones that were outside the space. So near perfect at learning specific examples, good generalizing within a cloud of points around that, and poor generalizing outside that space. I wrote it up in cognitive psychology after having some battles with reviewers we could talk about sometime later. And the conclusion was that the class of eliminative connectionist models that is currently popular couldn't learn to extend universals outside the training space. In my view, this is the thing that I am most proud of having worked on. Some details for later. This led me to some work on infants, and what I tried to argue is that even infants could make these kinds of generalizations that were stymieing the neural networks of that day. So it was a direct, deliberate test of the outside the training space generalization by human infants. So the infants would hear sentences like la ti ti and ga na na. I read these to my son yesterday. He thought they were hilarious. He's 7, or almost 7. And then we tested on new vocabulary. So there would be sentences like wo fei fei or wo wo fei. So one of those has the same grammar as the kids had seen before, and the other had a different grammar. Because all the items were new, you couldn't use some of the more statistical techniques that people thought about, like transitional probabilities, and it was a problem for early neural networks. And the conclusion was infants could generalize outside the training space, even where many neural networks could not, and I argued these should be characterized as learning algebraic rules. It's been replicated a bunch of times, and it led to my first book, which was called The Algebraic Mind. The idea was humans can do this kind of abstraction. I argued that there were 3 key ingredients missing from multi-layer perceptrons. The ability to freely generalize abstract relations, as the infants were doing. The ability to robustly represent complex relationships, like the complex structures of a sentence. And a systematic way to track individuals separately from kinds. We will talk about the first 2 today, probably not the third. And I argued that this undermined a lot of attempts to use multi-layer perceptrons as models of the human mind. I wasn't really talking about AI, I was talking about cognition. Such models, I argued, simply can't capture the flexibility and power of everyday reasoning. And the key components of the thing I was defending, which I would call symbol manipulation, I didn't invent it, but I tried to explicate it and argue for it, are variables, instances, bindings, and operations over variables. So you can think in algebra, you have a variable like x, you have an instance of it like 2, you bind it, so you say right now x equals 2, or my noun phrase equals the boy, and then you have operations over variables. So you can add them together, or you can put them together, concatenation if you know computer programming, you can compare them and so forth. Whoops. We got lost there. I don't know why that happened. Together, these mechanisms provided a natural solution to the free generalization problem. So computer programs do this all the time. You have something like the factorial function, if you've ever taken computer programming, it automatically generalizes to all instances of some class, let's say integer. Once you have that code, pretty much all of the world's software takes advantage of this fact, and my argument from the baby data was that human cognition appeared to do so as well, innately. The subtitle of that first book, and you can't see it that well here, was Integrating Connectionism and Cognitive Science. I wasn't trying to knock down neural networks and say forget about it. I was saying let's take the insight of those things, they're good at learning, but let's put it together with the insights of cognitive science, which a lot of which have been about using these symbols and so forth. And so I said, even if I'm right that symbol manipulation plays an important role in mental life, that doesn't mean we shouldn't have other things in there too, like multi-layer perceptrons, which are the predecessors of today's deep learning. I was largely ignored, I think, in candor until around a year or so ago. People, I think, started paying attention to the book again. But it did inspire a seminal book on neurosymbolic approaches, which I hope some people will take a look at, called Neurosymbolic Cognitive Reasoning. And I'm going to try to suggest that it also anticipated some of Yoshua's current arguments. I stopped working on these issues. I started looking at innateness. I learned to play guitar. That's a story for another day. Didn't talk about these issues at all until 2012 when deep learning became popular again. There's a front page story in the New York Times about deep learning, and I thought, I've seen this movie before. And I was writing for the New Yorker at the time, and I wrote a piece and I said, realistically, deep learning is only part of the larger challenge of building intelligent machines. Such techniques lack ways of causal relationships. We'll have interesting discussion about that today. They have no obvious ways of performing logical inference. There's still a long way from integrating abstract knowledge. And I once again argued for hybrid models, deep learning as just one element in a very complicated set of machinery. Then in 2018, deep learning got more and more popular, but I thought people were missing some important points about it. And so I wrote a piece. I was actually here in Montreal when I wrote it. It was called Deep Learning, a Critical Appraisal. It outlined 10 problems for deep learning. I think it was on the suggested readings for here. And the failure to extrapolate beyond the space of training was really at the heart of all of those things. I got a ton of flack on Twitter. You can go back and search and see some of the history. I felt like I was often misrepresented as saying we should throw away deep learning, which is not what I was saying. And I was careful in the paper to say in the conclusion, despite all the problems I've sketched, I don't think we need to abandon deep learning, which is the best technique we have for training neural networks right now, but rather we need to reconceptualize it not as a universal solvent, but simply as one tool among many. So the central conclusions of my academic work included the value of hybrid models, the importance of extrapolation, of compositionality, acquiring and representing relationships, causality, and so forth. Part 2, Yoshua, some thoughts on his views, how I think they've changed a bit over time, a little bit about how I feel misrepresented, and how our views are and are not similar. The first thing I want to say is I really admire Yoshua. For example, I wrote a piece recently skewering the field for hype, and I said, but you know, a really good talk is one by Yoshua Bengio, a model of being honest about limitations. I also love the work that he's doing, for example, on climate change and machine learning. I really think he should be a role model in his intellectual honesty and in his sincerity to make the world a better place. My differences with him are mostly about his earlier views. We first met here in Montreal 5 years ago, and at that time I don't think we had much common ground. I felt like he was putting too much faith in black box deep learning systems. He relied too heavily on larger data sets to yield answers, and he'll talk about System 1 and System 2 later, I guess I will as well. Felt like he was all on the System 1 side and not so much on the System 2 side, and I went back and talked to some friends about that. A lot of people remember a talk he gave in 2015 to a bunch of linguists who didn't like Yoshua's answers to questions like how would we deal with negation or quantification, words like every, and they felt like what Yoshua mostly did was to say, well, we just need more data and the network will figure it out. And if Yoshua were still in that position, I don't think he is, I think we'd have a longer argument. Recently, however, Yoshua has taken a sharp turn towards many of the positions that I've long advocated for, acknowledging fundamental limits on deep learning, need for hybrid models, the critical importance of extrapolation, and so forth. I have some slides and camera shots that I took at his recent talk at NeurIPS that I think actually show some really interesting convergence here. So, disagreements now. Well, I'll talk about my position, the right way to build hybrid models, innateness, the significance of the fact that the brain is a neural network, and what we mean by compositionality. And that's it. I think we actually agree about most of the rest. The first one's the most delicate, but I think occasionally Yoshua has misrepresented me as saying, look, deep learning doesn't work. He said that to the IEEE spectrum. I hope I've persuaded you that that's not actually my position, that I think deep learning is very useful. I don't think it solves all problems. The second thing is his recent work has really nailed what I think is the most important point, which is the trouble deep nets have in extrapolating beyond the data, and why that means, for example, we might need hybrid models. I would like, frankly, for him to cite me a little bit. I think not mentioning me devalues my contributions a little bit and further misrepresents my background in the field. What kind of hybrids should we seek? I think that Yoshua was very inspired by Daniel Kahneman's book about System 1 and System 2. I imagine many people in the crowd have read it. You should if you haven't. And that talks about one system that's intuitive, fast, unconscious, another that's slow, logical, sequential, unconscious. I actually think that's a lot like what I've been arguing for all along. We can have some interesting discussion about the differences. There are questions, are they even different? Are they incompatible? How could we tell? I want to remind people of what I think is one of the most important distinctions drawn in cognitive science, which is by the late David Marr, who talked about having computational, algorithmic, and implementational levels. So you could take some abstract algorithm or notion like I'm going to do a sorting algorithm. You could pick a particular one like the bubble sort, and then you could make it out of neurons, you could make it out of silicon, you could make it out of Tinker Toys. I think we need to remember this as we have these conversations. So we want to understand the relation between how we're building something, what algorithm is being represented. I don't think Yoshua has actually made that argument yet. Maybe he will today. I think that's what we would need to do if we wanted to make a strong claim that a system doesn't implement symbols. And Yoshua has been talking a lot lately about attention. I think that what he's doing with attention reminds me actually of a microprocessor in the way that it pulls things out of a register, moves them into a register, and so forth. And so in some ways it seems as if it behaves at least a lot like a mechanism for storing and retrieving values of variables from registers, which is really what I have cared about for a long time. Then I've seen some arguments from Yoshua against symbols. Here's something in an email he sent to a student. He said, what you're proposing as a neurosymbolic hybrid doesn't work. This is what generations of AI researchers have tried for decades and failed. I've heard this a lot, not just from Yoshua, but I think it's misleading. The reality is that hybrids are all around us. The one that you use the most probably is Google search, which is actually a hybrid between knowledge graph, which is classic symbolic knowledge, and deep learning, like a system called BERT, some people will know. AlphaZero, that is the world champion, or was until recently world champion of Go. It's just been succeeded, but very, very
Professor Marcus, you have 5 more minutes.
5 more minutes. AlphaZero is also a hybrid. OpenAI's Rubik's Cube solver is a hybrid. There's great work by Josh Tenenbaum and Jiyun Mao that's also a hybrid that just came out this year. Another argument that Yoshua has given is that lots of knowledge isn't conveniently represented with rules. It's true. Some of it's not conveniently represented with rules, and some of it is. And again, Google search is a great example where some is represented as rules and some is not, and it's very effective. Third argument is, or difference that we might have, and I don't fully know Yoshua's view, is about nativism. So as a cognitive development person, I see a lot of evidence that a lot of things are built into the human brain. I think we are born to learn, and we should think about it as nature and nurture rather than nature versus nurture. I think we should think about innate frameworks for things like understanding time and space and causality, as Kant argued for in the Critique of Pure Reason and Spelke has argued for in her cognitive development work. And the argument that I've made in the paper on the left is that richer innate priors might help artificial intelligence a lot. Machine learning has historically typically avoided nativism of this sort, and as far as I can tell, Yoshua is not a real fan of nativism. I'm not totally sure why. Here's some empirical data showing that nativism in neural networks works. It comes from a great paper by Jan LeCun in 1989 where he compared 4 different models, and the one that had more innateness in the terms of a convolution prior, for those who know what that is, were the ones that did better. This is just very quickly a picture of a baby ibex climbing down a mountain. I don't think anybody could reasonably say that there's nothing innate about the baby ibex. It has to be born with an understanding of the 3-dimensional world and how it interacts with it and so forth in order to do the things that it does. So nativism is plausible in biology, and I think we should use more of it in AI. Some of you may know, as I turn to brain and neural networks, that there was actually a cartoon about this debate by Dilip George. It's worth looking up on Twitter. And in the cartoon version of the debate, Yoshua wins by saying, your brain is a neural network. And everybody was, wow, I guess Yoshua was right after all. And Yoshua did, at least half in jest, make a similar argument to me on Facebook when he said, your brain is a neural net all the way. Of course, deep neural networks aren't really much like brains. I've been arguing that for a while. There are many cortical areas, many neuron types, many different proteins in different synapses, and so forth and so on. I actually heard Yoshua make essentially the same argument at NeurIPS last week, and so I think we probably pretty much agree about that. He made a beautiful argument about degrees of freedom in particular that I loved. But the critical question is really what kind of neural network is the brain? So going back to Mara's distinction, you could build anything you want, any computation you want out of Tinker Toys or out of neurons. We really want to know whether the brain is a symbolic thing at the algorithmic level or not, and then we ask, well, how is that implemented in neurons? So simply knowing that the brain is a network made of neurons doesn't actually tell us that much. We really want to know what kind of network it is. There's another argument. People say, well, symbols aren't biologically plausible. I think this is a ridiculous argument. When my son learned long division last week and followed an algorithm, he was surely manipulating symbols. We do at least some symbol manipulation some of the time. And back in the 80s, people knew this, and they said, well, symbols are the domain of conscious rule processing. They're just not what we do unconsciously. Pinker and I said, well, language isn't that conscious, and we use symbols in language too. The real question is not whether the brain is a neural network. It's how much of it involves symbolic as opposed to other processes. Even if the brain never manipulated symbols, which is counterfactual to our world, why exclude them from AI? We can't prove that they're inadequate. They have proven utility. Most of the world's computer code is written in it, and so forth. And importantly, lots of the world's distilled knowledge comes in the form of symbols. So, everything in Wikipedia is symbolic. We'd like to be able to use that in our machine learning systems. 5, compositionality. Yoshua has been talking a lot about compositionality, and I think he will tonight. I think he means something different than I mean by it. So I'll let him give his description later, but I think it's partly about putting together different pieces of networks and so forth. I'm really interested in the linguist sense, which is how you put different parts of sentences together into larger wholes. Here's a good example. Last week, my friend Jeff Kloon, I've been encouraging him to come to UBC and encouraging UBC to hire him from a job. And my friend Alan Mackworth said, good news, Jeff Kloon accepts. And I wrote back and said, awesome, he told me it was imminent, but swore me to
Professor
secrecy.
Marcus, you have 30 seconds.
30 seconds. Can I have 2 extra minutes?
Unfortunately, no.
I'm not going to be able to do the recursion. It's fine.
Give you 2 more minutes to everyone.
The gentleman from Montreal yields me 2 minutes. And so I said, yep, or Alan said, yep, I knew that you knew. And eventually we get to everyone in this room now knows that Alan knew, that Gary knew, that Jeff was going to accept the job at UBC. I don't think we can represent that in today's neural network. So we can barely get a system to represent the difference between eating rocks and eating apples. And this famous quote, you can't cram the meaning of an entire effing sentence into a single vector, I think still stands. Compositionality is not just about language, so it's also about learning different concepts and putting them together in different ways. Here's my kids inventing a new game. 10 minutes later, they've combined things that they know. Children can learn something in a few trials, and we haven't figured out how to do that yet. Synthesis, what I hope people will take away from this. Conclusions, the biggest takeaway from this debate should be about the extent to which 2 serious students of mind and machine have converged. We agree that big data alone won't save us. We agree that pure homogeneous multi-layer perceptrons on their own won't be the answer. We both think everybody going forward should be working on the same things. Compositionality, reasoning, causality, hybrid models, extrapolation beyond the training space. And we agree that we should be looking for systems that represent more degrees of neural freedom respecting the complexity of the brain. At the same time, I hope to have convinced you that symbol manipulation deserves a deeper look. Google search uses it, maybe you should too. That we've rejected it prematurely, that hybrid neurosymbolic models are actually thriving, and there's nothing more than prejudice holding us back from embracing more innateness. The real action in compositionality is understanding complex sentences and ideas in terms of their parts. AI has had a lot of waves of things that come and go. In 2009, deep learning was down and out. A lot of people dismissed it. I have a friend who saw Jeff Hinton give a talk when only one person came, or poster, excuse me.
You have 30 seconds.
Luckily, Bengio, LeCun, and Hinton kept plugging away despite resistance. I hope people doing symbols will keep plugging away. Here's my prediction in my last slide. When Yoshua applies his formidable model building talents, which I envy, to models that acknowledge and incorporate explicit operations over variables, magic will start to happen. Thank you very much.
Thank you, Professor Marcus. Non, je pense que je l'ai ici aussi. Regardez si je peux l'ouvrir sur celui-là. Sinon, on va brancher directement sur l'autre. Comme tant de brancher.
Ce serait mieux si c'était celui-là. Ce serait mieux si c'était celui-là.
Oui. Donc, ça devrait être correct. On va peser sur Play. Et le cliqueur est ici.
C'est ça. On peut le mettre en Presenter View. Oh merde, c'est du Keynote. Okay. On va prendre celui-là.
OK. Parce que là, ça va.
All right. So, welcome to this debate. And thanks, Marcus, for setting up and talking first. So I took a lot of notes. So the main points I want to make. This is not working. Let's see here. I want to talk about out-of-distribution generalization, which is connected to some of the things that Marcus talked about, which I think is more than the notion of extrapolation. I'll get back to that. I want to talk about my views on how deep learning might be extended to dealing with system 2 computational capabilities, rather than taking the old techniques and combining them with neural nets. I want to talk briefly about attention mechanisms and why these may provide some of the key ingredients that Gary has been talking about that make symbolic processing able to do very interesting things, but how we can do it within a neural net framework. And and then contrast that with some of the more symbolic approaches. So I want to get out of the way a few things about the term deep learning, because there's a lot of confusion. And especially when deep learning is a straw man, it tends to be used to mean MLPs from 1989, just like Gary used the term just a few minutes ago. If you open the last NeurIPS proceedings, you'll see that it's much more than that. So deep learning is really not about a particular architecture or even a particular training procedure. It's not about backprop. It's not about convnets, RNNs, or MLPs. It's something that's moving. It's more of a philosophy that's expanding as we add more principles to our toolbox to understand how to build machines that are inspired by the brain in many ways, and use some form of optimization, usually a single objective, but sometimes multiple objectives, like in GANs. In general, there's a coordinated optimization of multiple parts, and taking advantage of some of the early ideas from the 80s, of course, like distributed representations, but also more modern ideas like depth of representations, taking advantage of sharing computations and representations across tasks, environments, enabling multitask learning, transfer learning, learning to learn, and so on. And as I will argue, I think with the tools to move forward include things like reasoning, search, inference, and causality. To connect to neuroscience, because Gary mentioned that, there's actually a very rich set of work happening in the last few years connecting again the modern deep learning research with neuroscience. We had a paper just published in Nature Neuroscience called Deep Learning Framework for Neuroscience, but I won't have time to talk about it today. So out of distribution generalization, this means something different from the normal form of generalization, where we have data from one distribution and we worry about generalizing to examples from the same distribution. When we talk about extrapolation, Gary, it's not clear whether we're talking about generalizing to new configurations coming from the same distribution. So you have to think about the notion of distribution to be able to make a difference. For agents in the world, this is very important because what they see changes in nature because of interventions of agents, because of moving in time and space and so on. And what I've been arguing for a little bit now, certainly much less than Gary, is the importance of compositionality. But one of the things I've done in the 2000s is try to help figure out why even current neural nets, and the ones from the 80s with distributed representations, have a powerful form of compositionality. I'm not going to go into details of that, but this dates to about 5 years old, and similarly why composing layers brings in a form of compositionality. So basically my argument is we have these two forms already in neural nets. We can incorporate the form that Gary likes to talk about and I like to talk about these days, which is inspired a lot by the work of linguists. But I think it's more powerful and more general than just about language. It's something we use in conscious reasoning, for example. Basically what it is about is how one might combine existing concepts in ways that may have zero probability under the training distribution. It's not just that it's a novel pattern. It's one that may be unlikely under the kinds of distribution we've seen. And yet our brain is able to come up with these interpretations, these novel combinations and so on. And at NeurIPS, I gave this example of driving in a new city where you have to be a little bit creative in combining the skills you know in novel ways in order to solve a difficult navigation problem. Now, this issue is not new in deep learning. I mean, in the sense that people have been thinking about it at least for a few years, and actually would say it's one of the hardest areas in deep learning. And we haven't solved it, but I think people are starting to understand it better. And one of the ingredients which I and others have been thinking is crucial in this exploration is attention. So attention is interesting because it changes the very nature of what the standard neural nets can do in many ways. It creates dynamic connections that are created on the fly based on context. So it's even more context dependent, but in a way that can favor the sort of what Gary calls free generalization or something like this. That I think is important in language and in conscious processing. So why is that? So attention selects an element from a set of elements in the lower layer, and it sends the selected element in a soft way, at least the soft attention kind that we do in deep learning typically. And so the receiver gets a vector, but it doesn't know where that vector comes from. And so in order to really do a good job, it's important for the receiver to get information not only about the value that is being sent, but also where it comes from. And the where is sort of a name. Now, it's not like a symbolic name. It's, we use vectors, what we call keys and transformers, for example. And you can think of these as the neural net form of reference, because that information can be passed along and be used again to match some element to some other element to perform further attention operations. So this also changes neural nets from vector processing machines to set processing machines, which is something Gary talked about in his earlier interventions, and that I think that is important for conscious processing. So I've been talking a lot about consciousness in the last couple of years. There's, of course, a much richer volume of research in cognitive neuroscience about consciousness. And the way that I'm trying to look at this is how we can frame some of the things that have been discussed in cognitive science and neuroscience about consciousness and about other aspects of high-level processing, and frame them as priors, either structural or regularizers, for building different kinds of neural nets. So one of these priors is what I call the consciousness prior. It's implemented by attention, which selects a few elements of an unconscious state into a smaller conscious state. And in terms of priors, what it means is that instead of knowledge being in a form where every variable can interact with every variable, what this would entail is that at this high level of representation, there's a sparser form of dependency structure, meaning that there are these dependencies which you can think of like a sentence, like if I drop the ball, it will fall on the ground, which relate only a few variables together. Now, of course, each concept, like ball, can be involved in many such sentences. And so there are many dependencies that can be attached to a particular concept. But each of these dependencies is itself sort of sparse, involves few variables. So we can just represent that in machine learning as a sparse graphical model, a sparse factor graph. So that's one of the priors, and the reason why such a prior would be interesting is that it's something we desire for the kinds of high-level variables, factors that we communicate with language. So there's a strong connection between these notions and language. The reason being that the things we do consciously, we are able to report through language, whereas the things we don't do consciously, that are going below the level of consciousness, we can't report. And presumably there's a good reason for this, because it's just too complex to be put in a few simple words. But what's interesting is that if we can put these kinds of priors on top of the highest level of representations of our neural nets, then it will increase the chances of finding the same sorts of representations that people use in language. So I call them semantic factors. Another prior that I've been talking about has to do with causality and changes in distribution, because remember I started this discussion by how do we change our ways in improve our deep nets so that they can be more robust to changes in distribution. There's a fundamental problem with changes in distribution, which is that if we let go of the IID hypothesis that the test data is the same distribution as the training data, then we have to add something else. Right? This is something fundamentally important in order to cope with changes in distribution. Otherwise, the new distribution could be anything, right? So we have to make some sort of assumptions, and I presume that evolutionists put these kind of assumptions in human brains and probably animal brains as well, to make us better equipped to deal with those changes in distribution. And so what I'm proposing as a prior here, and really inspired a lot by the work of people like Shopkoff and Peters and others in Causality, is that those changes are the result of an intervention on one or a few high-level variables, which we can call causes. So there's this prior that many of the high-level variables that I'm talking about are causal variables. In other words, they can be cause or they can be effect of something, or they related to how a cause causes an effect. And the assumption here is that the change is localized, right? It's not that everything changes when the distribution changes. If I close my eyes, like here, or I put some dark glasses, there's only one bit that changed, just one variable changed its value, right? And we can exploit this assumption in order to learn representations that are more robust to changes in distribution. This is what I talked about in my NeurIPS presentation. And we can exploit that by introducing a meta-learning objective that says better representations of knowledge have this property that when the distribution changes, very few of the parts of the model need to change in order to account for that change. And so they can adapt faster. They can have what's called smaller sample complexity. They need less data in order to adapt to the change. Another thing that we have explored is related to modularization and systematic generalization, as the idea that we're going to dynamically recombine different pieces together, different pieces of knowledge together, in order to address a particular current input. So we have a recent paper called Recurrent Independent Mechanisms, which is one first stab at that. And I'm not going to go through the whole thing, but some of the main ideas is that we have a recurrent net. It's broken down into smaller recurrent nets, which you can think of different modules, which we call independent mechanisms. They have separate parameters. They're not fully connected to each other. And so the number of free parameters is much less than in the regular big recurrent net. Instead, they communicate through a channel that uses attention mechanisms, such that they can basically only send these named vectors, these key value pairs, in a way that makes it more plug and play, that the same module can take as input the output coming from any module, so long as they speak the right language, that they fill the right slots, if you want to think in a symbolic sense. But it's all vectors, and it's all trainable by a backprop. And there's also a notion of sparsity of which modules get selected in the spirit of the global workspace theory, which comes from cognitive neuroscience. All right, so let me list a few of these priors. I've already mentioned a couple, and others I had not really time to mention. So the consciousness prior, the idea that the joint distribution of the high-level factors is a sparse factor graph. Another one I didn't talk about, but of course has nice analogs in classical good old-fashioned AI and rules, is that the dependencies that I've been talking about are not dependencies defined on instances. It's not like there's a rule for my cat and my cat food. There's a general rule that applies to cats and cat food in general, right? And so we do these kinds of things, of course, a lot in machine learning. In graphical models, these date back to even the convolutional nets and dynamic Bayes nets, which share parameters. And so something like this needs to be there as well at the representation of the dependencies between the high-level factors. I mentioned prior that many of the factors at the high level need to be associated with some causal variables, or how causal variables interact with other causal variables. And in the same spirit, and I didn't have time to talk about it because it's really a whole other talk, but very closely related to this subject, agency. So we are agents. We intervene in our environment. This is closely connected to the causality aspect. And the high-level variables, if you look at the ones we manipulate with language, often have to do with agents, objects, or actions, which mediate the relationship between agents and objects. And there are a few papers already in the deep learning literature trying to use these priors to encourage the high-level representations to have those sort of properties. And of course, when you start doing things like reinforcement learning, and especially look at intrinsic rewards in reinforcement learning, these are concepts that come very handy.
Yoshua Bengio, you have 5 more minutes.
+2.
It's already done.
Ah, okay. So then there's this other prior I already mentioned, the idea that the changes in distribution arise from localized causal interventions. And finally, one that is connected to this one but is different and has been explored by my colleagues, for example, Leon Boutou and Martin Ajovsky and others before them, is the idea that some of the pieces of knowledge at the high level, or even at the low level, correspond to different timescales. There are things about the world that change quickly. There are things that are very stable, right? So there's like general knowledge that we're going to keep for the rest of our life. And there are aspects of the world that can change. We learn new faces, we learn new tricks. So this is something that fits well with the meta-learning framework, where you have fast learning inside slow learning. But I think this is another important piece of the puzzle. All right. Now, how is that related and potentially different from the symbolic AI program? Well, we would like to build in some of the functional advantages of a classical AI rule-based symbol manipulation in neural nets, but in an implicit way. So we need efficient and coordinated large-scale learning. We need semantic routing in system 1 and the perception action loop. We need distributed representations for generalization, which has been a big success for deep learning. We need efficient search that's based on system 1. We need to handle uncertainty. But we want to incorporate these other things I've been talking about that really have been explored first by the people in classical AI, like systematic generalization, factorizing knowledge in small exchangeable pieces, manipulating variables, instances, references, and indirection. And so this is connected to why I think just taking the mechanisms we know for good old-fashioned AI and applying them on, say, the top layer on the output of a neural net is not sufficient. We need deep learning in the system 2 component as well as in the system 1 part. We need those higher level concepts to be grounded and have a distributed representation to achieve generalization. We can't do brute force to search in the space of reasoning, and then there's the question of how symbols should be represented. My bet is that we can get many of the attributes of symbols without the kind of explicit representation of them, which has been the hallmark of classical AI. So we can get categories, for example, by having multimodal representations of distributions. We can use things like Gumbel softmax, which encourage separation into different modes. We can get indirections of variables, as I mentioned already. We can get recursion by recurrent processing. And we can get a form of context independence, which is allowing to dynamically activate combinations of mechanisms in a context-dependent way. I'm done. Thanks.
Professor Marcus, you have 7.5 minutes to answer.
Should I go over there?
Yeah, you should. You can answer there. Or you can.
Can I have my slides back to show a couple extras?
Yes, yes.
So I don't think we disagree on all that much, except for your last set of slides. Is it better if I do this? If I can, we're going to get my slides back up, AV again, after AI. So I didn't quite understand your response to Google search in a way. So I trotted out Google search as an example of a hybrid system that works in the real world, that scales, it's massive scale.
I didn't talk about Google search.
Do I? Well, yes, exactly. So your critique of the good old-fashioned AI hybrid system. So let me just say, good old-fashioned AI is symbols all the way. I'm not endorsing that, right? I'm arguing for you realize symbols plus deep learning. I take Google search to be an existence proof for things that you just said couldn't exist. So you said good old-fashioned AI is not going to be able to represent probabilities well. It's not going to scale
I don't understand
well.
why you talk about Google search. I'm not trying to emulate Google search.
I know you're not trying to.
I'm trying to get intelligence.
Hang on, just 1 second. Can we just go into back and forth instead of doing the 7.5 minutes and just be more freeform about it? So then,
15 minutes for both.
yeah, great. So right, you're not trying to build Google search. You're trying to build an intelligent system.
Yes.
Google search is in some ways an intelligent system, in some not. But I think you have two avenues here. You can either say it's so different from an intelligent system that it's not interesting, or you can say it's interesting and it does show the proof of concept to build a hybrid.
No, look, I completely agree that a lot of current systems which use machine learning also use a bunch of handcrafted rules and code that was, designed by people based on their understanding of the problem. This is how state-of-the-art systems, in particular dialogue systems, I think is even a more obvious example where current state-of-the-art systems combine machine learning and with a lot of handcrafting. It's also true of autonomous vehicles these days. I mean, there's a lot of engineering on top of all the computer vision. So there's no question. I don't think we disagree on this. The question is, where do we go next in order to build something that's closer to human intelligence?
Okay, so I may have misunderstood your argument. You're not saying, I'm going to recap to make sure I understand. You're not saying that one couldn't build hybrid systems. You're saying...
They already built.
That's what I was saying, but okay, then I misunderstood your argument.
No, I'm talking about how the brain works and how I would like to build AI in the future.
Let's come back to the brain part. So why are you not satisfied that hybrids are part of the answer? If I read you correctly...
It depends what you mean by the word hybrid.
So at what point do you get off the hybrid train?
So I get off the hybrid train when it's about taking the good old algorithms, like in production systems and ontologies and rules and logic, which have a lot of value and I think can serve as inspiration, and trying to take them, basically glue them to neural nets. So people have been trying to do these kinds of things for a long time. In the 90s, there was a lot of neural symbolic work and so on. And I've tried to outline in my last couple of slides, and I guess I misunderstood that I had 2 more minutes left, but I tried to outline the reasons why it couldn't work, and it's not just about how the brain works, but for machine learning reasons, for practical computational reasons. So one of them is search. So right now, what I mean by search is what we do when we have the knowledge in, say, things like rules or pieces of neural nets, and now we can dynamically choose which parts go with which parts in order to come up with a new conclusion. This is what reasoning and planning are essentially about. And if you introspect a little bit about how humans plan and how humans reason, we don't explore a zillion different trajectories of possible ways of combining things and then pick the one that works best according to some criterion. We essentially go and try one thing, and sometimes two, and if it really doesn't work, we try 3 or 4. Go masters go up to 50, okay, but like their brain is weird because they've been trained, or people who are really good at at arithmetic and so on. But like normal behavior involves this very intuitive sort of like we know where to search. And that's based on system one. That's based on something that we don't have conscious access to that knows where to search. And so that's one reason why we can't use the old algorithms. The other reason is that the symbols themselves, we need to represent information in a richer way. Like the reason why connectionists really wanted to depart from symbolic processing because they thought that it wasn't sufficiently rich kind of representation in order to get good generalization. You want to represent everyday concepts like words in natural language by sort of this sub-symbolic representations that involve many attributes. And this allows to generalize across similar things. And I've read some of the things you wrote, and you could say, well, these attributes are like symbols themselves. Sure, you could do that. But the important point is now you have to manipulate these rich representations, which could actually be fairly high dimensional. We need to keep that from the neural net world. Yeah, and of course we need to keep the things that have worked well in machine learning, which include representing uncertainty, which some people are doing, like Josh Tenenbaum with probabilistic programming and so on. So I think there are some efforts going in those directions, but we need to keep these ingredients together.
So I'm going to mostly emphasize our agreements here. I agree, first of all, that classical symbol systems have search issues. And I think that to the extent that one wants to preserve them, one wants to solve those problems. So there are ways that people have thought about it. For example, in psych, which is the kind of the classic, most huge symbolic effort, in psych there are micro-theories to target reasoning in particular domains. And that's, I think, an idea that's worth exploring. But I absolutely agree that if you have unbounded inference, you're in trouble. I think that AlphaGo is an example where you bound the search partly through a non-symbolic system, and then you use symbolic system there as well, and so it's kind of a hybrid in there.
In what way is it a symbolic system?
The Monte Carlo tree search is just, traversing trees.
It's a search, but there are like no symbols.
You have to keep track of the trees, and trees are symbols.
That
actually brings me to a separate line of discussion I'd like to have.
I think it's just a matter of words. Right? So search. That's where we need search, and so obviously, if we need some kind of search, if you want to call that symbols, I think symbols to me have a different nature. Symbols have to do with the discreteness of concepts, and this is also something that is important. But as I mentioned quickly at the end of my presentation, we can get discreteness not necessarily in its hardest form, in its purest form as you have in symbols. You can get discreteness by having in neural nets lateral inhibition that creates a competition such that the dynamics converge to one mode or another mode. This is what you observe in the brain, by the way, when you take a decision. There's a sort of competition between different potential outcomes, and so the dynamics chooses one sort of discrete choice over another, but it does it in a soft way, and the brain has access to all of that soft information.
I'm going to lay something else on you. I think that we both think the other side is strawmanning our baby. So I think you're strawmanning symbols because lots of people have put probabilities and uncertainty into symbols, and you think, and I think it's an interesting discussion point, that I'm strawmanning deep learning. So you said I'm attacking the models in the 1980s, and there's some truth in it. And then there's a question of what the scope should be. So I think both for symbols and for neural networks, there's a kind of question about what's the proper scope of them, and that we're actually pushing to the same place from opposite sides. So I would argue that the kind of deep learning stuff that was straight out of the 80s, which is continued until like 2016 in my view, but we could argue about that. Just let's have a big multi-layer perceptron, let's pile a lot of data in and hope for the best, which I don't think you believe anymore, but maybe you did at one point. That's one kind of deep learning. That's the kind of, I don't know, prototype or canonical version of deep learning, and you want to open deep learning to a whole lot of other things, and I think at some level that's fine, and at some level I think it's changing the game. And you might, I'll elaborate that in a second, I think that with respect to symbols, you might feel I'm doing the same. So I want to say, Sure, symbols. I want the discreteness of symbols, but I'm very happy to add in probabilities, like in a probabilistic stochastic grammar or something like that. I have no problem with that. I love a lot of Josh Tenenbaum's work, which is really like symbolic programs plus uncertainty. And so I want to expand the umbrella of symbols, and you want to expand the umbrella of deep learning. Why don't we say, let's build deep learning symbolic systems that expand the scope of deep learning and expand the scope of symbol systems?
Look, I don't care about the words you want to use. I'm just trying to build something that works and that is going to require a few simple principles to be understood. And I do agree that there's lots of interesting inspiration we can get today in the work that's been done in cognitive science and in symbolic AI. Yeah, I think that some of that needs to be reinvented. And by the way, we started doing things like attention mechanisms, and people were doing deep reinforcement learning already at the beginning of this decade. So it's not actually attention mechanisms even date from much earlier than that. So it's been around. And another thing you have to keep in mind, I've been working on recurrent nets since the 80s. And in a way, the various forms of recurrent nets, including the gated ones, use very similar principles, and again, have been around since the 90s. So it's not a completely new thing. There's an evolution, of course. We're doing research, so it's not like we have one algorithm and we're stuck with it. We're building and constantly trying to expand on the set of principles that we have found to work. There's nothing wrong with that.
Yeah, there's nothing wrong with that at all. I think we should actually yield to the questions from Vincent and the public.
Sure.
You want to answer Microsoft?
Sure.
Yes. I'll go there.
This might have been turned off.
If we want to turn it on, this one?
Is,
This one is on. So,
I'll stay here. I'm just going to grab water.
So the first question is for Professor Gary Marcus. Steven Pinker said recently in a tweet that it's a nature and nurture. So deep learning neural nets are in fact shallow, soaking up patterns but lacking explanation, causality, rule-based reasoning for novel and unique situations. What is the innate knowledge for deep understanding, and what needs to be learned along the way?
Sorry, and what needs to be done? I missed that.
What would be the innate knowledge necessary to have deep understanding instead of deep learning representation? You would like to have deep understanding. That means to be able to have causality, reasoning, and so on, and consciousness.
If I
Sounds
can
like,
riff
sounds
on
like
that
a question for
a
me.
Well, yes,
Can I riff on this slide for a second? I think it will bring something out that's interesting. So I made a slide that I didn't show, which I made a slide that I did not have time to show, which is both, has a picture of a great new paper by Yoshua that we had on the reading list that is well worth reading, that is about causality. And it's a very mathematical paper. I took what I think is some of the core math of it at the bottom. I will admit that I didn't read the paper as carefully as I wish that I had. But Yoshua is going after causality by trying to make some clever observations about how distributions change over time relative to interventions that are made, which is, of course, the classic thing that we try to do when we run experiments. And he's got, I think, some very clever ways of going after that within neural networks. And God bless him. I think it's great work. It's not the work that I would do, but I think it's terrific. I'm just going to draw contrast.
I'm not sure I want to use God's blessing, but it's okay.
Well, you got the gist of what I was saying. So on the right, I have something, can you just step aside? I have something, just so people can see the reference. I have something from a paper that Ernie Davis and I wrote. Ernie did almost all the hard work, but I helped a little bit. That most people in the field right now would find to be repulsive, but that I think we need to think about very carefully. Ernie created a logical formalism for understanding something very simple, which is containers. So I have water in this. If I tilt it, the water will fall out. What happens if I drop the microphone in it? Well, maybe not the electrical part of that, but just the physical reasoning about it. And the formalism that Ernie came up with that I think is responsive to your question is something that broke things into time, space, manipulation, things about rigid objects and the histories of objects. So he did a very careful analysis of the knowledge that one needs in order to do this basic thing. But it's not a trivial thing, because we use container metaphors for a large fraction of the things that we talk about. I don't want to say it's 50%, but it's significant. So for example, we can think of a container as a lake, we can think of a cup as a lake, we can think of as a container, we can think of the body as a container, and so forth. And the argument of this paper was that in order to be able to make inferences about these things, you need prior knowledge. And there's a question about whether that knowledge is innate or it's acquired experientially, but the argument is you won't be able to make these inferences unless you have this knowledge about sets and object-containing regions and have these kind of axioms and those kind of axioms, things about what rigid objects can do. And so one possibility here is we need the formalism on the left in order to acquire the knowledge on the right. Another possibility is we never need the kind of knowledge on the right. It never needs to be reified in the way that Ernie Davis proposed. My view is that we should have people working on both sides of the spectrum. People often think they're in the minority. I feel like I'm in the minority, but we can do the sociology later. I'd like to see more people working on stuff like this to build some broad frameworks for space, time, causality, and so forth. But I totally welcome the kind of stuff that Yoshua is doing, even if I personally don't have the skills to do it. And I think the empirical question is kind of, could you, from the bottom up, derive all this? Although I feel like maybe I strawman Yoshua. I thought that he was more anti-nativist than maybe he really is, because he acknowledged evolution. So I'll say one more sentence and then turn over.
Of course I acknowledge evolution. I mean,
well, I'll say one more sentence and then you can take it away. So in my view, what part of the field should be doing is saying, do we have innate priors around things like this? This is kind of work that Liz Felke does in cognitive development and René Baillargeon and so forth. And part of the field should be trying to reify that knowledge, and part of the field should be like, if we have that knowledge and we know something about causality, how can we learn from that?
So let me impersonate Jan Lequin for a minute. It's not that he and I and others with similar thinking think that learning has to be from a blank slate. In fact, we have theorems from the 90s, the no-freeness theorem, that clearly says you can't have learning if you don't have some priors, okay? But what we're saying is more subtle than that. What we're saying is we'd like to be able to get away with as little prior as possible. Now, how is little measured? Well, you can think of measuring it in bits. So if you think about how big is a program that would encode those priors, and you would zip that program, that would be how big the prior is. So the kinds of priors I've been talking about in my presentation, I was talking about priors, but these are priors that in a way are not going to require many bits. And so it's going to be easier for evolution precisely to discover those priors. Now, I also know full well that evolution has discovered very specific, strong priors. In fact, if you look at evolution, most of it is about completely hard-coded behavior. But these are not the behavior that are most adaptive. These are not the behavior that allow a species to adapt to, as well as humans have been able to do. So it's more interesting for me to think about the part of what evolution has discovered that is more general. These are the most generic priors. And of course, we have priors that are very, very specific. We kind of know how to see and to walk to some extent when we're born, and many animals have a lot more when they're born. So it's just a matter of what we care about here is trying to squeeze the prior knowledge into this, a few simple general principles as much as possible. We don't know where is the right line, of course.
So to use your language, you have a soft prior, which is that you want as little innate stuff as possible. I
have a meta prior, which I want as little prior as possible.
Right. So this is a place where we at least disagree in taste. Because I don't want a huge amount, but I think I want more than you. Of course, we don't actually have a number, but let me give you my intuition for why.
I wouldn't want to have to design the semantics of each of the boxes in an AI system like this. If I could get away with it, why not? Because, I didn't say why we want to have as little prior as possible, is because these lead to more general purpose machinery that can be applied to a wider spectrum of behaviors, environments, problems, and so on. It's as simple as that.
Well, I guess I got two things to say there, but one is actually from Jan's work, since you mentioned it. And we actually argued about this very thing the other day when we were at NeurIPS last week on a panel. In this particular empirical case, having more of a prior was actually better, right? So in this particular case, having a convolutional prior made the system better off. It did restrict the range.
It's a very small prior. It's like 3 lines of code of difference, right? It's not a big change in the amount of information compared to the classical computer vision that was done before ConvNets, where you had to design the functions by hand completely.
So let's say that it's 3 very brilliant lines, right? Jan shared the Turing Award with you for those 3 brilliant lines, in essence, right? They were hard-won, they were very clever, they've been very valuable to the world. Maybe, I got 25 boxes up there, they're 3 lines each, and we just need, 24 more discoveries of that magnitude. Is the genome big enough to encode all those 95% of our genes are involved in brain development. I think there's room in there to encode, that many, maybe 10 times more.
There's lots of room in the genome, but clearly not enough to encode the details of what your brain is doing. So it has to be that learning is explaining the vast majority of the actual computation done in the brain just by counting arguments. So like 20,000 odd genes with 100 billion neurons and 1,000 times more connections.
I have the other one I wanted to show. Oh, I do. So that was what this book was about, was what I call the genome shortage argument. The idea was we only have so many genes, let's say 20,000 genes. We thought it was 30 when the book was written. We have 86 billion neurons. And so what is the implication of that? So the genome shortage argument was, well, we have to learn it all. But I think that the more nuanced...
No. Nobody said you have to learn it all. Again, you're doing the straw man thing.
But let me give you the...
Nobody says that. Nobody in their right mind says that.
So, I mean, it's partly a question about what our bid is. I want to have 20 things in this debate that Jan and I had. I put 10 on the board, and he said none.
The things you put on the board, I agree with most of them. In fact, most of them, they are small priors. They don't require a lot of bits to be specified. So
those were things, since I don't have the slide up, those were things like spatiotemporal continuity as being innate.
Well, you have them in ConvNets.
Well, not the part about you could track an object over time, know that it still exists.
Well, it's user spatial continuity.
Right? It's related. I mean, it's really translational invariance. But and
it's actually more than
the other things I had on the list.
It's actually more than that because of the pooling. But yeah.
The other thing that I had on the list were things like symbolic priors. So operations over variables. Those I think you'd be less comfortable with.
I am totally comfortable with operations over variables. It's just that the meaning of operations and variables is different for me and for you, right? So I'm thinking of operations as little neural nets that do things that are not just discrete, that manipulate rich representations. And I think of variables as indirection, passing information about references, about keys, about the nature and types that can be rich rather than symbolic. But besides, I agree with the need for references, for example.
I mean, in a way, that's all I really want. So that you've made me a happy man. I'll tell you another time that you made me really happy earlier tonight. You talked about having reference without knowing where it comes from. And
no, I'm saying the reason you need reference is to be able to know where the value you're getting comes from. That's the reason these neural nets need to propagate not just values, but also names, except those names are going to be vectors as well.
You're more symbolic than I. I'm finding it harder and harder to disagree with you. We'll take another question.
The second question is for both Yoshua and Gary. So Montreal.AI talked to Jeff Loon. Jeff Loon said, 99% of machine learning community is focused on what Jeff Loon called the manual path to AI.
The what?
The manual path to AI. Manual path. Which is we manually identify building blocks of AI with the assumption that one day we will somehow put them all together. Do you think a higher fraction of our collective effort should be reallocated into the alternate path of AI generating algorithm that Jeff proposed, wherein we simultaneously meta-learn the architecture, meta-learn the learning algorithm themselves, and we automatically generate the training environment themselves?
Well, I like this question very much because I worked on this question in the early 90s with my brother Sami, and it was essentially the subject of his thesis proposal, of his thesis. And this was one of the first papers on meta-learning. We were trying to meta-learn a synaptic learning rule. We didn't have enough computational power to do this. And even now, I think in order to realize the kind of ambitious program that Jeff is talking about, we would need a lot more computational power. That being said, I think it's a very interesting and important investigation, and I was really amazed by the presentation, for example, that Blaise Aguirres gave at NeurIPS on this subject. I think this is very exciting. Personally, I'm also tempted by the desire to understand the principles that would be discovered, and so when I tried doing this meta-learning of learning rules, what I quickly realized is, well, you can't learn something like this completely in the abstract. It really helps a lot if you put in a bit of the right structure. And in order to do that, you need to do experimentation of the kind we do normally in machine learning, where you design the learning algorithm completely. And that helps to figure out what would be the right building blocks and the right inputs and outputs that are needed for learning a learning rule or learning a system like this. So I think, science is an exploration. We don't know what's going to work. These are two different directions, and they can coexist in a harmonious way.
I pretty much agree with Yoshua's answer. I'll answer it in a slightly different way. In principle, we know that evolution is a mechanism that's powerful enough to evolve minds because it evolved our minds. And having the machine do the work that sort of stands in for evolution would be great. In practical matters, it does matter what you're trying to evolve. And I think what has happened empirically in the evolution of neural networks literature is that people start with too little in the way of priors. And so they end up recapitulating some of our journey to bacteria, but not so much of our journey from, say, chimpanzees to human beings. In principle, we know it can work. In reality, having a tightly constrained problem and probably a bit of priors to help us there might help it work even better than it is. And I think it's totally worth exploring.
This one is for you, Yoshua. It's about the ethics of conscious and reasoning system. So there will be ethical implication about the conscious and reasoning system. How do you approach that?
I think it's important in general to ask the question of how our work as researchers will be used or could be used, because you don't need to go very far in the future. Today, we already see the misuse of AI in many ways, and I'm very concerned about how we are creating tools that can be destructive and endanger democracy and endanger human rights. So now the specific question of consciousness, I think, deserves a bit more time than this debate allows. Personally, I think that the kind of conscious processing that Gary and I are talking about are adding more computational power and intelligence to the systems that we can build. But I don't think it changes fundamentally the fact that we are building gradually more and more powerful systems. There's the question that some philosophers are asking about, whether we should eventually give personhood to intelligent, conscious machines. I don't think we're anywhere close to understanding these questions enough to be able to answer these sort of questions.
Thank you, Yoshua. For the next segment, our participant will answer a question from the audience, Erad Mila.
Thank you very much for this interesting debate, because artificial intelligence is going to solve a lot of problems that matter very widely to many persons. And I'm not a computer programmer, And so my question, I have several questions, but I'll limit it to two. One is that Gary Marcus, I don't know if you're Professor Marcus, said something that Professor Bengio's approach relied too heavily, or his approach to deep learning and his belief in it relies too heavily on larger data sets to yield answers. So why is that necessarily bad? There are large data sets and ways of constructing them. And do you want me to ask both questions at once?
Let's pause there, and I'll address that. First of all, I said that that was my impression of Yoshua several years ago. It's not my impression of Yoshua now. I think that he's doing a lot of exciting work, and he's right that some of it started a while ago. But my impression when I first talked to him, and I had friends at the linguistics conference, were when we would come to him and say, yeah, but the kind of systems that we have right now, they can't solve this. And I felt like his answer was often, when we get a big enough data set, we'll be able to cover that. And I had some quotes from the slides showing it. I think there are many people that are more extreme about that even than Yoshua ever was. So there's a branch of machine learning where I think people think the answer to a particular problem is really about getting the right data set. I think Tesla's approach to driverless cars is more or less like this. They say, we've got the most data, we have very cool ways, and they do, of trying to, for example, gather data about a particular kind of accident when it happens and so forth. It's very focused on the data and not so much focused on certain kinds of innovations in algorithm space that I would like to see. So I have no objection to gathering more and more data. I think that getting clean data is really, really important. People often underestimate the value of having good, clean databases, and I think the field was driven forward by having bigger databases. No problem with any of that, but the answers aren't just there. So in Yoshua's terms, you know, we need system 1 and system 2, and I would like to have more people working on system 2. Maybe we disagree a little bit about the execution of that, but I think we agree that we need some of that and not just the system 1 stuff plus bigger databases.
I want to say a few things about data, because I didn't answer this quote that you attributed to me. So I think that I'm interested in the small data regime to the extent that we also have a lot of data before we get to that point. So humans learn a new task after they've seen a lot about the world, right? There's no chance that you will be able to learn in a meaningful way without a lot of knowledge about the world that has been acquired previously. And so we need both large data in some sense. We need a lot of examples, if you want, for the baby AI to mature, and then it can face new tasks very quickly. So that's one thing. Also, more on the industrial side, if today, you know, I lead a company or a project, I'm going to use as much data as I can because this is the thing that works well. But at the same time, if you're looking further down the road in a few years and you're asking yourself what kind of improvement to our current algorithms would be most interesting for industry or for any kind of application, then looking at those transfer learning problems where you're looking at new tasks where you have little data, but you also have pre-trained on many other things, that's more right now in the research. So the two things are not incompatible. It depends on whether you are doing something in the short term or the long term.
I found just a tiny bit of something to disagree with Yoshua, but actually mostly agree with what he said. The one place where I disagree a little bit, first let me explain what a small data regime is, because not everybody will know what Yoshua meant by that. There are problems where people learn things with small amounts of data. Yoshua would say that's because they have a lot of experience elsewhere, and that's often the case. In any case, the small data regime is like, how do you learn something if you don't have 10 million data points? You know, if you're my kids and you learn a new game in 5 trials, how do you do that? And clearly some of it is you leverage prior experience. The only thing I'm going to add there is the reason that I did, and this is a half disagreement, is the reason I did that baby experiment back in 1999 was to show that there were some things that little kids could learn without much direct experience. So I made up the language, so they had no prior experience with the language that they did. I didn't say this, but the habituation, the period where they learned the made-up language, was only 2 minutes. So they only got something like 45 examples of this made-up language. So sentences like la ti ti and so forth for 2 minutes. And yet they were able to do this. And then somebody else, this is what happens in developmental psychology, if you show that kids of a certain age can do X, somebody else says, I've got even younger kids to do it. So somebody later showed that newborns could do what I had showed in the 1999 science paper of kids extracting rules. And so even newborns, it's not a perfect experiment, there's a control missing, but there's pretty good evidence that even newborns could do this. So in this particular case, I think that what you have to draw on is not experience outside the womb, but the experience that we get indirectly from evolution. So some of the problems that we solve in a small data regime come because we have priors for variables and things like that. Next question. No, I can't call on my friends. That's not fair. Someone else can though.
We have one here and after the, okay.
Thank you for your presentations. Dr. Marcus, you talked about the compositionality and the need to take into account the compositionality. From a linguistic point of view, we have debates and arguments on compositionality, but to make a simple system, we accept the compositionality. We had some progress in the neural nets, the recursive neural nets for compositionality. However, those efforts have been abandoned. They have abandoned the efforts on the recursive nets. We don't do research anymore on the recursive nets. And I think the argument is that we need the parse tree, we need the knowledge to feed into the recursive network to design the architecture and to form the network. I think there is a resistance here that the deep learning community, they are not willing to take any external knowledge in the form of linguistic structure or the parse trees. Dr. Bengio, would you please elaborate on that?
I don't think it's a resistance as much as an obsession to beating the benchmark, which could be good or bad, all right? It's because these very large, fairly simple architectures have been working so well. So, I mean, a good example now is the success of transformers. Transformers are working incredibly well, but they're using actually these key value pairs I was talking about. They're operating on sets. So, you know, the recursive nets was one attempt, but there's been others that have been more successful. And maybe recursive nets will come back. We don't know. The history of science is very complicated, as we've seen with deep learning. So I think there's a lot, actually, I don't read the sociology of the current deep learning field like you are. In fact, there's a lot of interest in exploring how we can put some architectural structure in neural nets that facilitate the manipulation of language and reasoning. And so I'm much more optimistic than you seem to be.
I would say that historically there has been a resistance. I think that that's changing some. I think it's partly a function of people have tools and they're good at particular things. And we don't really have, quote, deep learning tools, maybe in the extended sense, for really dealing well with recursion and compositionality in the sense that I'm describing it. I think there's much more hunger in that field in the last 2 or 3 years to do it. In terms of the transformers, I just gave a talk on a new benchmark called Dynamic Understanding at NeurIPS, and you can probably Google for it online. The basic point I made about transformers, like GPT-2, is they make very fluent speech, but they don't understand what's going on, or fluent text. So I just have an example here from a slide. So they're often plausible in the first few sentences of surrealist fiction, basically. So I fed into one of the systems across the street from NeurIPS, 2 unicorns walk into a bar, and then the system says, continues that passage with, at least that's what my picture shows. I've never seen such a multicolored, beautiful forest of sapphire eyes on the same corner of the street in a bar before. And it's like fabulous that it has created this surrealist prose. On the other hand, when I force it into the nonfiction genre, it seems a bit ridiculous. So maybe we can, I don't know if this is going to work or I'm going to lose it. An example I had on the right is 2 lemurs walk on a road. I was actually in a place with lemurs and roads recently. And another joins in. The total number of lemurs on the road is, and you're supposed to add up 2 and 1 and come up with 3. And if you're a human, you probably do that. But if you're a deep learning system, you might come up with something like not 100 is claimed, but about 80 or so. And so the system doesn't convert, and it goes back directly to your question, the prediction statistics that it's making about plausible classes of words into a direct representation of the individual entities that are involved. And so if you want to watch my benchmark talk, it's full of examples like that. Actually, I have them on the next slide. So I gave things about conventional knowledge, definitions, transformations, atypical consequences, and so forth. And then I have data from these models on the right, and they're typically doing like 30% or 10% or something like that. So there are sharp limits, and I think those limits come because we don't have kind of a parse tree on the output yet, and we need to do that.
There was another question. Unless you want to answer.
Go ahead.
Well, my name is Mr. Berry. Since Turing 75 years ago, and it's a virtual machine, and all we could do with the binary mathematics, we've achieved great things. Now today, we're with quantum computing and quantum computers, which are closer from the way that the human brain thinks. Something can be right or wrong, or it can be both, almost at the same time or at the same time. Well, quantum computing and quantum computers, could they represent a breakthrough that we were waiting for to achieve the artificial intelligence the best way?
Maybe so, but I'm a big fan of Occam's razor. So if we can build intelligent machines and explain how the brain works without having to go quantum, I think it's very satisfying to go for simpler solutions. And I think in terms of neuroscience, most of the community thinks that the brain can do its computation without requiring. Of course, there's quantum computing in the sense that molecules are operating in a quantum way, but if we abstract one level up, it's all computation, and that is not quantum by nature. So, of course, we don't know what I don't have a crystal ball, but at this point, I think the majority of the community, both in neuroscience and in computer science, are betting on traditional computing in the sense that it's not quantum. But and another thing I want to say is, right now, there are not many algorithms that can be efficiently parallelized by quantum computing, and no serious machine learning algorithms like deep nets and so on. If they can find the right theoretical breakthroughs that enable to implement things like deep nets in a way that takes advantage of the quantum capabilities, then it would change the game. It hasn't happened yet, but this is something that we can look for.
I pretty much totally agree. My friend Sandy's going to ask a question.
I'm going to start my question with a little anecdote. When a bunch of journalists went and interviewed the scientists who created the nuclear bombs, one of the things that they profoundly stated was they were so involved in the science, they didn't even think of the ramifications. So I'm listening to you two geniuses here, and I'm not even going to pretend that like 3/4 of this isn't SpaceX going right over me. But one thing that disturbs me is I don't hear a single word about checks and balances and ethics that are going into your creating the algorithms that are going into all of this, AI. And as somebody who's not in AI, who is a human in this world, I find this incredibly disturbing. I'm sure Gary has heard me say stuff like this before, but I'm bringing it out again because I would love to hear you guys address this.
The first thing I'll say is, of all the people in the field you could have leveled that accusation against, I think Yoshua is the least appropriate, because I think Yoshua thinks pretty deeply about this, and I'll let him speak about his version in a moment. My own version in the book Rebooting AI was to argue that common sense could be a way of building a framework such that machines could represent values. So you can think about Asimov's laws. You want robots to not do harm to people, and one of the things we talk about is how do you get a computer to even think about what a harm would be to a person? So it's one thing to get a computer to recognize a picture of an elephant after you've seen many other pictures of elephants, but you can't really do the same trick for harm, because harm takes many, many different forms. It's not really about the way that the pixels fall on the screen or the page or whatever. And so a lot of the argument that Ernie Davis and I gave about this particular set of issues was we need to rethink how we get knowledge into these systems and the nature of knowledge as a platform to then get to be able to program in the values that we want. So that's how we thought about it. I don't think it's a full answer, but it is how we thought about it. And I'll turn it over to Yoshua.
Thanks for raising that question. It's very important. Gary and I have been talking about maybe something a little bit technical from your point of view about where we think AI research should be going in terms of how we build smarter machines. But it's at least as important that our society invests even more on the question of how we're going to deploy these things. What is the responsibility of everyone in the chain, from the researcher to the engineer to the people doing auditing or to governments drafting regulations, to make sure that we steer our boat in a direction that's best for humanity, that's best for citizens. And I'm very concerned that we're building tools that are too powerful for our collective wisdom. And I'm fine with slowing down the deployment of AI. I think governments are not yet ready to do the proper regulation, and we need to spend more time talking about things like how AI can be abused to influence people, to control people, to kill people. These are all very serious issues. Discrimination, killer drones, advertising, social media, deep fakes. Basically, right now, it's the Wild West, and we need to quickly get our act together.
Maybe that's what you two should be working on.
Maybe we will. I'll just give one last example, or one brief example.
I want to mention that here in Montreal, we've been really working hard on this question, and we came up last year after 2 years of work involving not just scholars but also citizens with a thing we call the Montreal Declaration for the Responsible Development of AI. I invite you to check it out online, and we're pushing these ideas to the Canadian government. There's been many frameworks that people have developed around the world to try to think about the sort of social norms that we need in this deployment of AI. Now I think it's a lot in the hands of governments and the agencies that are looking at specific sectors where this technology is being deployed. It's also in the hands of the UN if it involves, for example, military deployment. And for that to work, we need the media, we need people to voice their concerns.
I'll just add one thing, because I think we have to go to the online questions. But I wanted to amplify the point about Wild West. A good way to think about this is right now, a driverless car manufacturer can basically put anything on the road. We can sue them after the fact if they cause great harm, but there's no regulations, essentially, about what you can do with a driverless car. And if you compare that to how much trouble there is to perform a new medical test or build a new drug and how much regulations there's an asymmetry that I don't think makes a lot of sense. And I'll give a shout out to my friend Missy Cummings, who has a podcast, I think with Azim, I'm blanking on his last name, forgive me, begins with an A, Hazar or something like that, Exponential View or something like that, a few weeks ago talking about this issue, the asymmetry in regulation between what's required for health and what's required for AI. I think Yoshua and I agree that there needs to be a lot more there. Questions from the international audience now?
Yes, for the last segment, our participant will answer a question from the international audience.
I'm not sure, you want me to read the question?
I think you're supposed to pick a question.
Pick a question.
So what we will do is that I will project question from the audience on the screen. Not
Those screen.
Oh, you're still on my slides.
Yeah. So I will be projecting the question from the international audience on this screen.
Stand by once again for AV.
I will give you a mouse to scroll and so on and to choose the question.
All right. part.
I'll just scroll down.
I'll do very quickly symbols while Yoshua picks the next one. Sure. What's my definition of symbols? I don't think we should waste time arguing about that. I think that from the perspective of symbol manipulation, the real question is, do we have operations over variables? You can define a symbol in such a way that it encompasses everything or nothing, and I don't think that's where the debate should be.
So there's a question about what is the chance of AI possessing self-consciousness? I think this is a very interesting question, but it's also very loaded, because we all have our own ideas of what consciousness means. We think we have something special. What I can say is it's something, fortunately, that scientists in neuroscience, cognitive science, and machine learning are starting to think about, and hopefully we can remove some of the mystery and magic from there, so we can be better equipped to answer these kinds of questions later.
So you can scroll down and up.
I don't know how to scroll.
Oh, I see. Yoshua is driving a mouse here, but it's maybe not working or something.
It's like a mouse. If you just do
This is now, there's AI, AV, and human interface.
Oh, I see.
There's the mouse wheel.
There's no mouse wheel. That's
They
the
don't
problem.
give you an affordance. That's how.
I see. Okay. These questions are too long. What is the best way to reproduce the levels of conscious and unconscious thinking in AI? That's what we've been arguing actually about. And the answer is we don't know. And that's why we need many different researchers to explore different ways of doing this.
Gary Marcus thinks that deep learning and symbolic AI are compatible and can provide the best of both worlds. Is there any evidence? I think that the best evidence that we have for that is we have some people building actual hybrid models in the real world that do useful things. None of them achieve human-level intelligence. You know, no deep learning system does that, no symbolic system does that, no hybrid system does that. But systems like Google Search do something that's relatively intelligent and help us, and they're very much hybrid systems. And then you have results like the Josh Tenenbaum and so forth results that I showed briefly, where at least in a very controlled environment, a hybrid system can beat a deep learning system or a symbolic system on its own. It's still an open argument. I don't think in the end that either Yoshua or I would say we have the answers here, right? We're trying to lay out what we think the territory is that people need to explore. And I think the biggest take-home message, as I said on the slide, is we actually agree a lot about what that geography is that needs to be explored. We have some differences about where to go in that exploration. Neither of us think that we've reached the destination by any means.
So I want to talk about the question about, you think language understanding is a form of intelligence. We clearly need better language understanding for AI, and there are really interesting connections between language, understanding, and reasoning, but they are really different. So I listened to a presentation at the last Europe's by Ev Fedorenko, and she's a cognitive neuroscientist. And what she found with her colleagues is that there's a language area in the brain, and it does process everything that's connected to language, but it doesn't do the other things that one might think are related to language, like reasoning. So it's other areas that are doing it. And that's also connected to the bigger picture of language that I've been talking about. Language has sort of syntactic aspects and structural aspects, but the semantic, what language is referring to is, people call common sense and grounded language understanding, refers to general knowledge of how the world works. And this is an area which is very active in machine learning. People, irrespective of whether they do language or not, are looking at how learning systems which interact with their environment can build better models of the world. And if we don't do that, we'll never have good language understanding. So this connects with some of the things that Gary talked about with limitations of transformers. I mean, transformers work incredibly well. These are the best things we know right now in order to process language in quantitative benchmarks. But as you said, they have, they make what I call stupid mistakes. And I think one of the missing ingredients is they don't have a world model. They don't, I mean, they might build quite a bit actually of world model through reading text, but there's a lot about the world which you can't get, I think, just from reading text. And maybe this is a place where Gary and I could disagree. Like, I think that there's a lot of knowledge about the world which is intuitive, for example, intuitive physics, that is difficult to put in words. I mean, of course, physicists do it, but babies don't do it. They have an intuitive understanding of physics. So in order to do good language understanding, I think that we need machines that understand how the world works in a physical sense, in an intuitive sense, and these two things need to be tied. And that's connected to the link between System 1 and System 2 that I was talking about.
I think we could probably talk for the rest of the time about this one question. There's a lot of interesting things there. I think the first thing that I will agree with Yoshua, and I've lost track, this is tracking identity over time. Language and reasoning are clearly separate things, but they're not fully separate. So there's wonderful work, for example, from Mike Tannenhouse and John Truswell showing experimentally that people reason about the world at the very moment where they're processing it. So if I give you an ambiguous sentence, you will look to what are the things out there in the world that can help me to disambiguate the sentence, and you will reason like, is there a cup on the table or a cup on the towel, and I'm going to put these all together in an understanding of a sentence. And so it's hard to draw a sharp line, Ev's interesting work notwithstanding. Sure. There's certainly overlap. On the other hand, a very clear example of how important all the physical reasoning stuff would be any primate that's not a human, right? Think about all the physical reasoning that a chimpanzee can do without any language at all. We could argue about the ape language studies, but I don't think they're very compelling. So you have species that can, navigate their way through trees and have social interactions of all very complicated social interactions, exchange, and all of these things without any language. And I think we would both be thrilled if, before we leave this mortal coil, we were able to build AI systems that could do what chimpanzees do. Now, I have a personal interest in language, having studied it for most of my career, and so I'd really like to see us get language right. I think having the world model is a prerequisite, and it's really hard.
Let me talk about this question about reasoning. How do you define reasoning, and why do you think deep learning will or will not be able to solve it? So of course, people have been tackling reasoning for a long time, and well before neural nets, became hot and considered as potential tools for reasoning. The way I think about how deep learning can do reasoning is connected to what I mentioned as these dynamically recombinable pieces of knowledge that we can search through. So we can search through how which piece of knowledge can be combined with which piece of knowledge in order to find an answer to a question. And those searches are heavily guided by our intuition, so we know where to search. And so reasoning is about looking for coherent solutions to a problem, to a question. There's an older way of thinking about reasoning which I find really, really appealing, which dates back to the early 80s neural network of Jeff Hinton with Boltzmann machines, where you can think of reasoning, you can find it again in modern graphical models. You can think of reasoning as finding a configuration of the random variables, the variables that maybe provide answers to your questions, that is most compatible with everything you already know, right? Which has the highest probability given all the facts you're giving to the machine. And with Boltzmann machines, you're trying to find that through a Markov chain which searches in the way that it does it is by looking for a low energy configuration, by gradually changing the configuration until you find something that is good. And I think something like this could make sense for the kind of unconscious reasoning that we do. We all have the experience of asking ourselves a question, not getting the answer back right away, moving on to something else, and then maybe the day later, the morning after or something, the answer comes to you. So the thing that has happened during those hours is happening in the background, and it's something that we don't, it's harder to characterize, but it may plausibly be this kind of energy minimization. Now, the kind of reasoning that we do consciously is very different. We don't consciously experience going through thousands and thousands of possible configurations. We immediately search through a few things that happen to be very relevant. So I think we need the two kinds of reasoning.
I think, again, we agree on the two kinds of reasoning. You could think about what you called 80s deep learning networks, and I call pure deep learning. And I would say those can't do certainly what you call system 2 reasoning. I would say that right now the best system for doing system 2 reasoning is the much maligned psych. And people might want to look at an article in Forbes where psych is given Romeo and Juliet and not straight text, but put into computer interpretable form, and you could argue about whether that's fair. But it's given Romeo and Juliet, and it can make some interesting inferences about characters' motivations and so forth. And that's a symbolic system. And I would say that the richness of inferences that can be made by symbolic systems is for now ahead of deep learning, but I will also grant Yoshua.
But it doesn't work.
Well, I mean, in a narrow domain, I mean, actually in many narrow domains it can work to some extent. I certainly don't want to say that it's the answer, but it's a proof of concept that you can do sophisticated reasoning.
It's very unlike
I'll give you a second to come back.
And it's very unlike how the brain does it. Your brain doesn't go through zillions of, trajectories.
I will agree
right?
on that point, but hold on. The contrast that I want to draw is, so we have a system that doesn't really, I think, do reasoning at all, which is a pure deep net, multi-layer perceptron with none of the attention.
So I disagree. I mentioned the Bose machines. They do just that.
They're not going to be able to make reasoning over quantified statements and so forth, at least not that I've ever seen.
Well, they haven't been explored recently, but this is essentially what they were designed for.
We can place a public bet afterwards about Boltzmann machines and their ability to deal with quantification, every sum, and so forth. I would say, by and large, that the results of extant neural networks on reasoning are not as impressive, even as that example from psych. But I would also say, I was going to give you the point and then we can come back, that if you take the broader notion of deep learning that Yoshua would like to defend, and you start putting in mechanisms for attention and indirection and so forth, which come at least a little bit close to the things that I want, then all bets are actually open. We don't know yet what the boundaries are once you include mechanisms like indirection. We know some of the things we can do there. There's a lot of stuff in classical reasoning I don't think has really been addressed yet. There are other people that are more expert in that, but I would say even just dealing with quantified sentences, how do you deal with everybody loves somebody and the ambiguity in that? We haven't really seen that yet.
So there's a question here about what do you think of transferring structured rules in the form of first-order logic onto network parameters as opposed to encoding the information in latent variables? So this is actually the kinds of things that people were trying to do in the 90s, trying to create a direct analogy between, or presentation, mapping between representations of knowledge in the weights between neurons and the rules in logic. And personally, I don't think this can work for a number of reasons. On the other hand, what I think can work, and in a way we're already doing it, is neural nets that can acquire knowledge by reading documents, just like humans do, or reading databases, like knowledge bases. And so this is something, of course, that we can do a lot better, because right now I don't think we have the right tools for this, but we're making progress. And the kinds of things that people are using now, transformers, I think can be evolved into what we need, especially if we couple them with better world models. So yeah, this is...
It's clearly still an open question. I think the most interesting work right now is done by, or some of the most interesting work in that specific question is done by Arturo Garces, who's trying to build hybrid models where you have explicit representation of logical formalisms and you can map it onto a deep learning system. It's still, I think, early days for that work, but it's interesting and it's another perspective here.
To make sure that those initial injected assumptions will still hold after the training, overcome catastrophic forgetting. So I think so the first question, I think we just, at least I gave a partial answer to this. The second one about forgetting is very important. It's connected to some of the things I was talking about when I mentioned factorizing knowledge into pieces, so that when there's a change in the world, a change in task, a change in distribution, a new piece of knowledge gets added, it doesn't it doesn't require the whole system to be adapted, but only a few parts of it that explain that change. And if we're able to do that, which for now we've done on a very small scale, but if we're able to do that on a large scale, then I think we can overcome catastrophic forgetting. We can build systems that adapt in just the necessary ways without having every neuron and every weight trying to be part of explaining the change that just happened or a new task.
If I could push some of Yoshua's fantastic students who are probably sitting in the room to study one question that they might not be studying so much right now, it would be that first question here, how to inject knowledge into deep learning models and frameworks. There are a lot of people in the field thinking about this. I don't think there are a lot of people thinking about it at the psych level.
We had a paper a few years ago that does the things I was talking about earlier, in the sense that we have a language model that while it's reading text, for example, like while it's reading a question or trying to complete a sentence, is looking up in a knowledge base, a structured knowledge base with you know, like subject, object, verb, things like this, standard relational databases, and looking for those words that it has seen or their equivalent synonym representations in the knowledge base, and then using attention mechanism, picking the pieces of knowledge in the knowledge base, which can help it predict what the next word should be. So this was done with Sung Jin Han, and it's been published. And what it allows is models that can do their normal neural net-y thing, but as they're computing, it's like they're allowed to go online and check for information that they don't already know, that is not already integrated into their inside brain, and use that information in order to answer questions or predict something.
I'm going to raise a technical issue and make an advertisement. So the technical issue is, I wonder how well, you don't have to answer it now, but how well it works with quantified statements and negation as opposed to triples, which, you know, things in first
I don't know. So at
logic
that
are
time,
harder.
we were not looking at that. And I think it's only recently with attention mechanisms in the form that involves indirection that you can start thinking about quantification. So quantification, the way I interpret it in a neural net sense, is essentially that you have these little modules, which in your world you would call rules, and that's fine, except they are not symbolic rules. They're just more like they're allowed to do inference on some variables given other variables. But the inputs of those rules don't have to be always the same, coming from the same place. So the inputs have types, just like functions in programming, in C++ have types. And so they expect their input to have the right type to match together, and when a rule matches what is in the data, it can be triggered, just like in production systems.
Well, so I'll get to the advertisement in a second. If we could work on one thing together, that would be it. The advertisement is Vince and I are going to put together a set of readings after the debate so people can follow up on some of the issues that we've talked about today. And my first nomination is the paper that you just suggested.
Okay, so if we are to build real-world AI systems, how feasible is the current practice of training deep learning networks end-to-end, knowing fully well that they are going to be huge in this regards? So for me, the end-to-end thing is mostly a problem when you consider biological plausibility, because there's a long delay between information being propagated from one part of your brain, say in the back, to the front part of your brain. So the number of back and forth exchanges that can happen in the time that you are able to answer a question, like half a second, is very short. It can go like back and forth a couple of times. And so it would be reasonable to assume that although there is coordination at a global level, a lot of the learning involves local effects. And so there's been a lot of interesting work in deep learning. I don't think it, right now, we've solved this problem where people are trying to predict the gradient that would eventually come back if you were to do end-to-end learning, and then use that to start the learning in a sense. And if you look at reinforcement learning systems, they use that kind of trick as well to predict the reward that you will get and use the predicted reward as an intermediate local reward. So I think there are some interesting questions about decentralizing this kind of learning. There's also more pragmatic explorations and things like federated learning, where people are trying to build deep learning systems that can learn on local nodes, like on people's phones and things like this, without having the data on those phones necessarily traveling to some central repository. So I think this raises all kinds of interesting questions. There's also a lot of interesting connections to multi-agent learning. So one of the hot topics in machine learning these days is how do we have multiple neural nets interact with each other, each learning from its own objective function, but in a way there's a social thing going on where they're together trying to solve a problem. So I think that's another way that you can decentralize the learning that humans do in society, of course.
I think we're almost out of time. I'll add one thing to that, and I think Vince maybe goes next. I think that modularity, in the sense that Jerry Fodor was talking about once upon a time, of having individual components that are tuned to particular things, is the heart of how the brain works. It's not fully modular, but I think the most amazing thing about the imaging literature, taking pictures, scans of people's brains, is the way in which the brain, now I'm going to connect to a phrase of yours, dynamically reconfigures itself in the course of anything that we do. So you can tell someone who's coming into a scanner experiment, like the ones that Ev's going to do, okay, what you're going to do now is you're going to take glasses and you're going to put them on the head every time you hear the word blue. And then people, in the space of 3 seconds, dynamically reconfigure their brain in order to be able to do that. I don't think that end-to-end deep learning is capturing that, but some of the dynamic reconfigurability that Yoshua is
But that is deep learning
for.
too.
Say again?
That is deep learning too.
I mean, there's some deep learning there. I mean, again, one...
No, it is
one
deep
tool.
learning. Seriously.
Deep learning that allows you to do the reconfiguration?
Yeah.
In what sense?
It's just deep learning with gates. We've had gates since 1989 or something like this.
Gates, I'm with you, and we can argue about the
Well,
definition.
of course we've made progress, but I mean, it's not really a completely new idea of gating computation. Neuroscientists have been talking about neuromodulators forever. So just remove from your brain the idea that deep learning is a 1989 MLP with feed-forward connection. That is not deep learning. Sorry.
We can argue about the scope. I will end with the agreement, which is I think that gates are the solution. So the question was framed in terms of end-to-end deep learning. And end-to-end deep learning typically is the closest thing to the kind of thing that I'm critiquing. Doesn't typically have
not the
gates
state of the
work.
art, not today's deep learning state of the art. That's not how it is.
I'm all for the gates.
Distinguished participants, ladies and gentlemen, we just had a hugely impactful AI debate. Many thanks to Gary Marcus and Yoshua Bengio, and to Mila for hosting us.
And many thanks to Vincent.
Thank you.
I want to thank Vince for even having the idea to do this, and for Yoshua for being gracious enough not only to do it, but to host it.
The conversation will continue on social network with the hashtag AI debate. A decade that has revived the field of AI is ending with this AI debate. A new decade will soon begin with the best way forward for AI. Stay tuned for the announcement of follow-up events and for the unveiling of the next Montreal.AI world-class event. Good night, everyone. Yeah, sorry. Thank you so much. That was great. Thank you, Gary. Thank you. Thank you, Joshua.